Hello, am I audible? Hello, who is this? 3197826. Hello, who is this? So, hello, everyone. Can you please unmute yourself? So it will be good to have a discussion. I'm sorry for being late today. Uh, so this is the last session of this course, and I have some good questions for you. So, so this is the last session that is mostly on fluidized bed and packed bed reactors. So there are basically two types of reactor that was discussed in the last session last week, that are uh, two main types of reactor where a catalyst are filled inside the reactor in a way that they are packed bed reactor or fluidized bed reactor. And there was a discussion on different shapes of bubble. So we have different shape of bubbles, and we had a discussion on that in the lecture. So let's look at it. Let's look at few questions. So first question is, in an elliptical bubble length of major axis is 16 centimeter and minor axis is 1 centimeter. What is the equivalent diameter of the bubble? Options are 4, 2, 1, 3. All of these are already discussed in the lecture, and we just need to uh, use one formula, and it's a very easy question. So I think you will be able to do it. So we have So we have so the formula for this for the calculation of equivalent bubble diameter is already discussed in the lecture. So the equivalent bubble diameter is 2 into a square b to the power 1 by 3. If the bubble is elliptical, then a is the 2a is the length of major axis and 2b is the length of minor axis. So here major axis is 16 centimeter. Therefore, 2a is 16 and 2b is 1 centimeter. So a is coming to be 8 and b is coming to be so 1 minute. I think it is the other way around. Yeah, 2a is the major axis and 2b is the minor axis. So 2a is 16 and b is, so I think it's 2 centimeter. Just to correct it. Uh, so the question is 2 centimeter. So b is so it is 2. So b is 1 centimeter. So equivalent diameter comes out to be 2 into a square b. A is 64 and b is 1 to the power 1 by 3. So there is something wrong with the question. So major axis is 16 centimeter and the minor axis is 2 centimeter. That is correct. And options are, we have to check the options. I think options are also, so I think this is the other question. Should be 8. Okay, so the correct question is this. So the equivalent bubble diameter is 2 into 8 into 8. So this is 2 to the power 3 into 2 to the power 3. So it comes out to be 8 centimeter. So the correct option is this. Okay. The next question is, in an elliptical bubble length of major axis is 1.5 centimeter and E value is 0.6. What is the equivalent diameter of the bubble? So options are 1.265, 2.53, 1, and D is 2. So that is again a formula based question. We know what E is. So E is nothing but B by A. And length of major axis is 1.5 centimeter, which means 2a is 1.5. So a is 1.5 divided by 2. And e we have, so we will get b. B is nothing but ea. So b is ea, and so the equivalent diameter becomes 2a e to the power 1 by 3. So 2 into 1.5 divided by 2, and e is 0.6 to the power 1 by 3. And if we calculate it, so it will become 1.5 into 0.6 to the power 1 by 3. I have to check. 0.6 to the power 0.33. That is 0.8345. And so it is coming out to be 1.2518. 0.6 power 0.33 into 1.5. So it is 1.26. So it is 0.8448, and so it is 1.2673 centimeter. So this is this. Okay. Next question is, in fluidized bed, height of the bed is 30 centimeter. Solid fraction is 35%. Solid density is 2500 kg per meter cube, and air density is 1.6 kg per meter cube. What is the pressure drop across the bed? So delta P is epsilon S G H rho P minus rho F. So epsilon S is 0.35. So 0.35 into 10 into height of the bed is 30 centimeter. So it is just the balance of the gravity with the bind force. So that is the pressure drop that is there. So rho P minus rho F is the pressure drop that is coming from there. So rho P minus rho F is 2500 minus 1.6, and therefore after calculating it, what we get is 2.623 kilo Pascal. Okay. So let's look another question. So the question is this: which So the question is calculate the pressure drop. Hello, am I audible? Who is this? Can you just say a few words so that we can connect and discuss few things that we are discussing right now here? We will do the pressure drop of air flowing at 30 degrees centigrade and 1 atm pressure through a bed of 1.25 centimeter diameter. Spheres at a rate of 60 kg per minute. The bed is 125 centimeter dia and 250 centimeter height. This question for you. The porosity of bed is 0.38. Viscosity of fluid is given to be 0.0182 centipoise. Density is given to be 0.001156 gram per cc. Okay. Calculate the pressure drop across the bed. So this is a very important question in terms of a packed bed reactor, and we need to calculate the pressure drop across the bed. So the thing is, first we need to check whether the flow is laminar, turbulent, or in transition. And how will we going to check that? By calculating the Reynolds number of the packed bed. If the Reynolds number, so we are having certain conditions through which we will check that whether the flow is laminar, turbulent, or in transition. And in case of laminar flow, we have to use Blaise-Cosny equation. In case of turbulent flow, we have von Karman equation, and in between the transition, we are having a Eigen equation. So we are having certain set of conditions. Based on that, we need to uh, uh, we need to understand that which equation will give the correct pressure drop across the bed. So so the conditions are packed bed. So this is basically a conceptual question as well as numerical, and based on that, we will be going to solve it. So basically, packed bed Reynolds number and type of flow. Okay. So this is the table that you should keep in your mind while having this kind of questions in order to solve it. So first is that if REP, I'm just say that's a packed bed. If it is less than 10, then the flow is considered to be laminar. If RE is in between 10 to 100, then it is a transition flow. So that is transition from laminar to turbulent. And if it is greater than 2000, then it is turbulent. Okay. So we are having this different kind of flows. And if we are having a which equation, so I will also extend this to this table in a way that we should know equation that is giving delta P. Delta P should be calculated using which equation. So in this case, we are having a laminar flow. So we will be going to use Blaise-Kosin equation. So that is the part of Argon equations. That is one part of the Argon equation, which we called as Blaise-Kosin equation. In transition region, we will be going to use Argon equation. And for the case of turbulent flow, we will be going to use I am a bit confused with the name, just 1 minute. And yeah, that is called as Burke-Plummer equation. So I sort of mistake when I'm saying that it is not a one carbon equation, it is Burke-Plummer equation. So these are the part of Argon equations. So I will show you that which equation will, which is what. Okay. So Blaise-Kozni equation is, I think it's already discussed in the lecture, but I'm just repeating for solving this question. So Blaise-Kozni equation is delta P, that is for laminar flow. So delta P is 150 L, that is height of the packed bed. V, that is the superficial velocity, viscosity into 1 minus epsilon square divided by Ps square dp square into epsilon cube. Okay, so V is superficial velocity of fluid. L is height of packed bed. Ps is sphericity. So for a spherical particle, it's going dp is diameter of the particle. Epsilon is void fraction. So this are the variables in which delta P depends, and this will be there for all the different kind of equations. Okay, so that is for laminar flow. For turbulent flow, we will be having a Bulke-Plummer equation. That is for turbulent flow, and delta P is coming out to be 1.75 L into rho into V into 1 minus epsilon divided by Cs dp epsilon q. Okay. And adding these two equation will give me a Argon equation that should be used for the case of transition region. So delta P, so for transition region, that is Argon equation. That is for transition flow. So delta P is coming out to be 150 LV mu into 1 minus epsilon. I'm just simply adding these two parts. Fear square, dp square. I think I have already discussed some sort of some questions based on the laminar and this bulky member and Blaise-Kozni in, I think, fifth or sixth part of that. Okay, so uh, you can also go through it. Some very good great questions were there based on sphericity also that I have already discussed. I think recording is already uploaded, so you can go through it. So this is for the case, as I told, that is laminar flow. And okay, so I think the equations are correct. Rho is using here. Okay. And rho should be there and rho is of fluid. Okay. So where there is a rho that is of fluid and rho and mu viscosity is of fluid. So that should be made clear. No, that's correct. So rho is not there. Mu should come in Blaise-Gaussian equation. Yeah, that is there. It should be b square. Let me check. In Berke plumber, it's b square. Mu is already there, right? So mu is already there. So mu is already there. Mu is there everywhere. And Berke plumber, you are saying, okay, let me check. So Berke plumber, yeah, it should be u square. Thanks for the correction. So it is b square 1.75 into L into rho u square into r minus epsilon divided by phi s into dB into epsilon q, and that is also square. I have sort of missed this also. Okay. So yeah. So let's do this question. First, we need to find out the Reynolds number packed for packed bed Reynolds number. And that is u, that is superficial velocity, rho f into dp divided by 1 minus epsilon into mu. So that is, we don't know what the superficial velocity is. We know density, other things we know. So we need to find out it. So the flow rate is, so what is given here is 60 kg per minute. So that is mass flow rate is given. I think it should be there. Uh, Let me check again. 1.75 rho u square L 1 minus epsilon divided by epsilon cube into dp into phi s. P into dp. Yeah, I think. Yeah, correct. Okay. Yeah, that's correct. Thanks. So we need to find out the velocity. So for finding out the superficial velocity, we need to find out the volumetric flow rate. And for that, first we need to we can relate volumetric flow rate with the mass flow rate. So mass flow rate is given to be 60 kg per minute. So volumetric flow rate is nothing but mass flow rate divided by density. So that is mass flow rate is given to be 60 kg per minute. So in terms of second, it is 60 kg per 60. So that is kg per second. And density is given to be 1.156. So density in kg per centimeter cube is in kg per meter cube. It is 1.156. Okay, so that is 1.156 kg per meter cube. Okay, so that is so 1 gram per cc to that is equivalent to 1000 kg per meter cube. So what we get is 1 divided by 1.156. And so on calculating it, we got what we get is 0.865 meter square per second. So velocity is q by a, and so that is 0.865 divided by pi by 4 dp square. So 0.865 divided by pi by 4 into diameter of the particle, that is 125 centimeter diameter. So 125 centimeters and centimeters, so it is 1.25 square, and so therefore it is 0.5 meter per second. So Reynolds number is becomes so superficial velocity is 0.705 into density of fluid. So density of fluid is 1.156 divided by, so this density is of fluid, so I should write into diameter of the particle. So diameter of the particle is 125 centimeter. So that is 1.25 divided by 1 minus epsilon. So 1 minus epsilon, the bed porosity is given as 0.38. So that is 1 minus 0.38 into mu viscosity is 0.0182 centipoise. So in centipoise to 10 minus 3. So on calculating, it is coming out to be 903. So from this, we are in this region. We are in this region, and so we need to apply Ergun equation to get the. So RE is 903. Therefore, we need to apply Ergun equation in order to get the pressure drop. Okay, so delta P into Vs into dP into epsilon cube divided by L rho V into 1 minus epsilon is nothing but 150 by RE plus 1.156 7.5. So I'm just rewriting this equation. If you take it, if you divide the coefficient of 1.75, you will get this as 150 by RE and delta P into this. So that is the Argan equation. That is sort of making as if Vs is particle R sphere, so Vs is 1. So I think you should try the calculation and then I will tell you the answer. Can you just let me know the answer? Uh, I don't know what's your name. So number is coming. So can you just tell me the answer? I will check and let you know if it is correct. So what's the reason for not calculating? Like, okay, anyway, you just have to apply this formula. Everything is ready, and the correct answer for this is delta P is 2492.92 Newton per meter square. Okay, so I think that's the concept that is there. The main concept is this, that you should know what is going on here. You need to calculate the packed bed Reynolds number, and that's you should use correct formula for that. Whatever the packed bed Reynolds numbers. This this is superficial fluid velocity. So that is V is everywhere the same. L is the pack height of the pack. Okay, so I think I have done some of the numericals that are important according to this week. Now let's look at some of the conceptual MCQs. Okay, so first question is, so this is question number 5. And the question is this: which reactor is favored? Is favored if efficient contacting in a reactor in a reactor is of prime importance. So that is Okay. So the fluidized bed, packed bed, anyone, any or none. So this is a easy question. So can you just answer it? Maybe on chat or wherever. What is the reason for using fluidized bed? Any reason for using fluidized bed? That's correct. So the correct reason is this interfacial contact area is high and okay. So I will so fluidized bed with because interfacial. No, no, one minute. But the reason is okay. So I'm sorry. Fluidized bed is not a correct option, and the reason is being interfacial contact area is same in both the cases anyway. The packed bed or the fluidized bed. Why you are thinking that the fluidized bed has a high interfacial contact area? Because the packing, if you have the same kind of packing and everything is same, the only thing is one is fluidized bed, another is fixed bed or the packed bed. I can write fixed bed, fixed bed reactor. So for me, the answer is fixed bed reactor, and the reason is this. So basically, in case of fluidized bed, the the particles will flow with the flow, fluid flow, and therefore the contact is not that good comparative to the packed bed, where the the bed is remain stagnant, and you will be having a good uh, bed. Okay, so so the reason is in passing to fluidized uh, in passing through fixed bed, and this reasoning I am taking from the Lemon's wheel, that is on chemical reaction, that is CRE, that is the book on CRE. Okay, so 1 minute. Okay. So in passing the gas through fixed bed, gases approximately behave like subplug flow. So gases approximate. It is quite different with bubbling fluidized bed where the flow is complex and not passing. This behavior is this behavior is unsatisfactory in terms of contacting and requires much more catalyst for high gas conversion and greatly depresses the amount of intermediate which can be formed in series reaction. Therefore, fixed bed is favored. Bed is favored where contacting is important. So, are you able to understand this explanation? If not, just uh, tell something like what is the issue. Then I will fix that. I'm sorry with the way, the way I have explained it before, because the correct explanation is this fixed bed reactor. Okay. So next question is, so is there any issue with this explanation? Like I don't know your name, but can you just give me answer on the chat box? Do you think that is not correct? The fixed bed of the fixed bed reactor. Okay, thank you. So let's look at another question. So the question is this: which reactor type is favored if the reaction is highly exothermic. Okay, that is again the options are same: fluidized bed, packed bed, both, or none. Do you want to answer this with whatever reasoning you will be having? Fluidized bed, gas velocity is higher, fluidized, then packed. Mm, but like if the reaction is highly exothermic, therefore high rate of convective heat transfer. Okay. Anything else? Yeah, you are going in the right direction, but uh, do you want to say with that why not packed bed? That is true that whatever the reason for this case is true that you are having a higher convection rate of heat transfer, and that is sort of uh, managing the heat transfer rate easily, and therefore the heat produced from the reaction is balanced by the convective heat transfer in a way, and therefore the reaction is sort of isothermal in case of fluidized bed reactor, and that's why we say fluidized bed reactor. When we are having a highly exothermic reaction, we have to use fluidized bed reactor instead of packed bed reactor. And there are other reasons behind this is because so some reasons, as you mentioned, I'm just taking your points because you said it right. So we are having a rapid mixing of mixing of solid in fluidized bed manages heat transfer, and then we are having and sort of having a isothermal conditions. In case of packed bed, the issue is this, that there may be a hot formation of hot spot or moving hot fronts are likely to develop. Therefore, a packed bed is not preferable in this case. The last question is which reactor is good to use when we need to regenerate when we need to regenerate the catalyst, or when we need to treat the catalyst frequently because it deactivates rapidly. And options are again fluidized bed, packed bed, both or none. Okay, so what you are saying? How can hot spots be prevented in packed bed? Let us say I require good contacting, like in the previous question. That's a good question, but like uh, hot spot. So basically, it's a trade-off between. So you, it's the basically the priority that you want. So the if you are having a priority that hot spots won't be there, so you should use a fluidized bed. Maybe there will be a low conversion, but you should use a fluidized bed, which will which will help in having because if you will use packed bed and therefore there will be a hot spot formation definitely, and though there will be a good contacting, but there will be a hot spot. So it should be a trade-off between the two priorities, uh, whether you want a good contacting or what will be that depends on what is your priority, like whether you want a good contacting or whether you want a good uh, whether the reaction is exothermic. If the reaction is exothermic, you should directly go for fluidized bed. Uh, the efficiency may not be that much, but because you want to avoid because the reaction is exothermic and you want to avoid this uh, formation of hot spots, so that's why fluidized bed is recommended. Okay, so last question. So you have given the answer. So fluidized bed, since I cannot connect a regenerator to the fluidized bed, whereas in packed bed, it is more like a batch operation and not practical due to rapid deactivation. Uh, so what's the answer? Like fluidized bed or the packed bed? Because uh, okay, and what's the reason? Oh yeah, okay, you are writing. Sorry, I read it. I cannot. Okay, yeah, that's correct. Because in fluidized bed, it is easy to regenerate. It is easy to frequently change the catalyst, and therefore the correct option is fluidized bed. Okay, so all these things are there. If you are having any particular doubt, you can ask. But I think this is enough for week based on the week 8 discussion. Okay, so the last question is very straightforward. Why you we want fluidized bed? So that is easy. So if you are having any more questions, you can ask. Otherwise, we'll wrap up this session. Do you have anything else to ask? Yeah. I think I have shared all the sessions except the sixth and sixth is also there. I think, yeah, within 2-3 days, I will be sharing whatever is not there. I will check and share. Anything else? There was nothing much discussed in the last session because it's completely based on theory. It's a very conceptual thing. So I have just discussed few theoretical questions in that. Anything else? Okay. What's your name, by the way? If you want to know, tell you. Okay, Shravan. Okay, good. So yeah, we'll wrap up this session, and if you want anything, we'll discuss it later. Okay. If it's all fine, you can leave the session. I will also leave the session. I have further doubts. Oh my God. Yeah, you can ask me here only. What are the doubts? If you are asking me that when, how can I contact again? So you can always mail me. Whatever your doubt is, I will solve it. And if you want, we will meet. So my mail ID is shreyyank20@itk.sa.in. I will write it here also. You can always feel free to write to me. If anything you wanted to discuss right now, we will discuss it for sure. There is want. Okay. So can we end it?